I'm back. This is what keeps happening today. So, um, if you're someone who's reporting the stream, please stop. Um, all right. So, um, let me remind you what I was talking about. So we have a potentiometer. A potentiometer is essentially a variable resistor. We have a speaker, which is just plays sound. This is called a photoresistor. Okay, and a photoresistor is it's a resistor that depends on light level. So if the light level changes, the resistance changes. So it's kind of cool. And this is an example of. So if you make a resistor with this weird line thing on it, that is what is called a thermistor, which is a temperature sensitive resistor. So the resistance depends on temperature. Okay. And I think I already gave you this one, but this is a light bulb. Okay. Which is more or less like a resistor. So let me give you a cool circuit that uses some of this stuff. Okay. So what if I had a circuit that has, it's a voltage divider, and it has a potentiometer and then a bulb. Okay. And so I'm not really going to do any calculations with this, but the idea is, well, you might recall that with the potential divider, the bigger resistor gets more voltage. So if this is a 100-volt battery, if the top resistor gets 25 volts, then the bottom resistor is going to get 75 volts. Okay? So let's suppose that the resistance of the potentiometer goes up. What that means, because this resistance increased, that means that its share of the voltage is going to go up. Which means, and because both of these voltages have to add to 100, the bulb's voltage is going to go down. So the voltage across the bulb is going to go down. And what that means is that the bulb is going to dim. So this is basically a dimmer. All right. And then another example of this is, let's suppose we have a battery, and maybe the battery has a resistor connected to it, and then a thermistor, like so. All right. And let's suppose that the temperature goes up. So if the temperature goes up, then it turns out with thermistors, when the temperature goes up, the resistance goes down. So the resistance of the thermistor will go down. Hey, Aiden. And when the resistance of the thermistor goes down, that means that its share of the voltage is going to go down as well. So the voltage across the thermistor is going to go down, which means that the voltage across the other resistor is going to go up. Okay? So that means, so basically, if we were monitoring the voltage across this other resistor, we would be able to tell what the temperature is by looking at its voltage. Okay? So that means that we have a thermometer. This is basically how a thermometer works. Christian is asking a question, why does a higher temperature result in lower resistance? That's a good question. Basically, remember how current flow is determined by how many electrons are available to conduct the current. And if the sample is hotter, that means that the atoms are jiggling around more, which means you'll have more electrons are bumped free of their nuclei, which means that they're free to roam around. So the increased jiggling releases more electrons, which then means you can have more current flow more easily. So that's why it happens. Okay, so I'm going to do one more just qualitative example of this. Let's suppose I have a current divider circuit. Okay. All right. Oh, I have another question. How do you decrease the voltage of the thermistor? The voltage across the thermistor is changed by the temperature change. All right, I think I'm back. So let's suppose, I apologize, sometimes my upload rate is fluctuating a whole lot today, so I don't know. Today is just not a good day for technical issues. All right. So I'm going to answer Michael's question here. Why do thermistors change resistance with temp compared to normal resistors? Good question. All resistors have a slight variation in resistance with temperature. But with a thermistor, you are making the resistor out of a material that has a really strong dependence on the number of electrons that are released with temperature. So it depends on the material that you make it out of. So going back to this example, so the resistance of the potentiometer goes up, which means that this branch has more resistance, which means that the current in the left branch is going to go down. More resistance means less current. And so that results in two things happening. One thing is, because the total amount of current is constant from this current source, if the amount of current going through the left branch goes down, then the amount of current going through the right branch goes up. Okay? And if the current going through the right branch goes up, that means there's more current flowing through the speaker. And so that means that the speaker will get louder. Okay? So the speaker is going to get louder when you turn up the potentiometer. And similarly, because the left current goes down, that means that there's less current for the light bulb, which means that the bulb gets dimmer. So you can see that when you turn up the resistance of the potentiometer, the speaker gets louder and the bulb gets dimmer. So the music comes up and the lights go down. So I call this circuit the Romancer. Okay? It's hardwired. It's just you turn up the knob and those two things happen. All right. So now we're going to get to kind of the new content for today. And so the new content is what's called real batteries. Okay. And so the question is, what happens in this circuit? So you have a circuit with a battery and nothing. So you might say, well, current is volts divided by resistance. Okay. So you might say, well, the resistance is 0, so you have V divided by 0, which is equal to infinity amps. So I'll put exclamation points there because that's supposed to surprise you. No battery can send out infinite amps. It's just not possible. Okay? So something's going on here. There's actually resistance in the circuit. One place that resistance comes from is the wires themselves. You know from the lesson the other day that resistance is rho L over A. So wires have some resistance which prevents the current from being infinite. And another thing is that batteries themselves have a resistance. Okay? So it turns out that a real battery is a real battery is you can think about it. So here's the extent of the real battery. And a real battery can be thought of as an ideal battery, so a battery that could output an infinite current and then in series with a resistor. Okay? And so the voltage of the real battery is called the EMF, which is denoted by curly E. Okay? And the resistance of the battery is called the internal resistance, which is denoted by little r. Okay? So let's just do an example here. Let's say we have a real battery of EMF 6 volts and internal resistance 1 ohm. Okay? And so this is the real battery right here. This is a real battery. Okay? and the real battery is connected to a resistor. And so let's say that this is a 10 ohm resistor. Okay? Actually, let's make the internal resistance 2 ohms. Can I do that? I can. So what I want to do is I then want to redraw the circuit, taking into account the fact that this is a real battery. So the real battery is actually a 6-volt ideal battery in series with the internal resistance. Okay? So the internal resistance is 2 ohms, and then this is 10 ohms. So this is the real battery. Okay? If I want to find the amount of current that flows, the current that flows is going to be V over R. And if the voltage is just the 6 volts. But the resistance, we also have to include the resistance, the internal resistance of the battery. So the total resistance is 2 ohms in series with 10 ohms, which is 12 ohms. So that means that our current is going to be 0.5 amps. Okay? If we were to neglect the internal resistance, then we would get I equals V over R equals 6 over, neglecting the internal resistance, we only have 10 ohms of resistance, so 6 over 10, 0.6 amps. Okay? So you can see that when we account for the fact that it is a real battery, we always get less current. Less current with a real battery. And in this case, so the question is, well, when can we neglect the internal resistance of the battery? And you can neglect the internal resistance of the battery when this internal resistance is small compared to the other resistor in the circuit. Okay? So 2 is not so small compared to 10, so I would say you need to worry about the internal resistance in that case. But if this was 2 ohms and that was 1,000 ohms, then you don't have to worry about the difference between the two. Or you can neglect the internal resistance. Okay? There's an important concept called the terminal voltage of the battery. The terminal voltage, which is equal to the amount of voltage the external resistor gets. Okay? It's the amount of voltage the external resistor gets. And the external resistance, so we would do that with just the voltage is I times R. And if we think about it, how much current does the external resistor get? The external, this is all a series circuit, and according to SIPEV, series things get the same current, parallel things get the same voltage. So this is a series circuit, so the external resistor is going to get 0.5 amps. The external resistance is 10 ohms. So that means that the terminal voltage is 5 volts. Okay? Notice that this is less than the EMF of the battery. Okay? So the lesson, or the general lesson here is when you have a real battery, A real battery will output less current than you expect, and it will have less of a voltage than you expect. It'll give less of a voltage than you expect, okay? So real batteries are not as good as ideal batteries. That makes sense. All right, well, I'm going to hop over to Discord, and I hope to see you there. If you have any questions, I can help you with the daily items, etc.